numerical and graphical limits. Okay, so the definition of a limit is if f of x becomes close to a single value L as x approaches c from either the right or the left, then the limit of x as x approaches c is L. So mathematically the limit is written as the limit of f of x as x approaches c is L. And so basically what that means is that, let's say I have my graph here, and I have the x value of, let's say, 1. Now to find the limit of this function f of x as x approaches 1. And so what I would do is I would look to the left and to the right of 1 and see where my function is approaching. Let's say I could draw some arrows right here to represent. So you can see that my limit of f of x as x approaches 1 is at this point right here. Let's say y equals like -3. So here you have this table of x squared minus 2x minus 3 over x minus 3. And for our x values, we have values that are approaching 3 from both the left and the right. And as you can see, f of x is undefined at 3. So when you're finding the limit, you're not finding the actual value of the function at that point, but you're finding where the function approaches. See here, these little ticks right here, this minus means you're approaching from the left. This plus means you're approaching from the right. And when there's nothing here, it means you're approaching from essentially the left and the right. So you can see in the table, we have at x equals 2.9, f of x is 3.9, 2.95, 3.95, 2.99, 3.99. So you can see this f of x value is approaching 4 left. You can see that. And same thing goes for the right. You have 4.1, 4.05, 4.01. It's approaching 4 from the right as well. And since these equal each other, that means the limit of this function as x approaches 3 is 4. As you can see, this graph here turns out to just be a straight line. What it doesn't show you is that at this point here, there's a hole and it's undefined at this just this point. But you can see as you're approaching from the left and from the right, this function is approaching 4 right here. Now let's try another one. For sine x over x, let's fill in the values here. At 0 itself, the function is undefined. Here we have 0.99, 0.999. You just use a calculator for this, you wouldn't have to do this by hand. You can see we both approaching from the left, approaching from the right, and approaching from both sides here. So as we approach from the left, you can see we got 0.99, 0.999, 0.9999, and that value is really approaching 1, as you can see right there. Same thing from the right, we have 0.99, same numbers, it's also approaching 1. And so the limit of sine x over x as x approaches 0 is 1. Another graph here. You see, at this point, the function is undefined, so it doesn't have a value. But you can see as it approaches 0 for both the left and the right, the function approaches 1. It's not actually at 1, but that's the definition of a limit. The limit is like, the function approaches 1. So like, if I covered this part, if I didn't know what this was, like, what do I think would be the point right here? sometimes limits will not exist. For example, there's different left and right behavior. So when you're approaching from the left and you're approaching from the right, you do not get the same number. The limit does not exist. Unbounded behavior. So if you're approaching like infinity from one side and negative infinity from the other side, the limit also would not exist. And oscillating behavior. F of x oscillates between two fixed values as x approaches c. I'll show you an example later. But if you want to show the limit does not exist, you basically write D N E, all caps right here. It means does not exist. So here is the different left and right behavior. You see, as we're approaching 3 from the left, we approach 5. As we're approaching 3 from the right, we approach 1/2. And since these are not equal, the limit does not exist. Because there's a break here. Here's another example. This one's also different left and right behavior, but it has to do with the infinities. This is 1 over x. And as you can see from the left, as we approach 0, as from the left we approach negative infinity. From the right we approach positive infinity. And since they're not equal, the limit also does not exist at x equals 0, as x approaches 0. Here's an example of that oscillating behavior. This function is sine of 1 over x. And at 0 itself, it's because it's 1 over 0, this function is undefined. But it's impossible to define a limit here, because it just oscillates over and over and over again between -1 and +1. It oscillates an infinite amount of times between these 2 points. And so it's impossible to define a limit at that location. That would also not exist. Alright, let's try something else. This is the absolute value of x over x. So you see we have this break here between the left and right sides of the function. So this is asking us for the limit of f of x as x approaches 0 from the left. So as x approaches 0 from the left, you can sort of draw an arrow to visualize it. The function's at -1. Now this is from the right. You can draw an arrow from the right. This is at +1. So the limit of f of x as x approaches 0, it does not exist, because the limits from the left and from the right do not match. Let's try another one. This is 1 over x squared. You can see that it approaches infinity from both sides. So as it approaches 0 from the left, see the function's approaching infinity. As it's approaching from the right, it's also approaching infinity. And so the limit as x approaches 0 would be infinity, because these values right here match. Alright, last one. We did this awkward piecewise function here. So you may remember this dotted line right here. These are vertical asymptotes. These circles that are not shaded in, they are holes. The function doesn't exist at these locations. Now these dots right here, the function does exist at these locations right here. So let me show you. So f of 0, you go to x 0 and try to find where the function is. It's right here because that dot I was mentioning, it's at -4. The limit of f of x as x approaches 0 from the left. This is from the left specifically. So as you approach from the left, you can see you're approaching a value about, let's say, that's about 3/4. This doesn't actually exist at this location, but you can see the function, like, if you covered this up with your hand, then you would see, like, oh, this would probably be 3/4 right here. Alright, now this is asking for the limit of f(x) as x approaches 0. As you can see from the left, it approaches about 3/4. From the right, however, it approaches -4. Since they're not equal, that means this limit does not exist. Now f of 1 here. So we look for 1 on the graph. You see this right here is a hole. But there's this dot up here. This is the actual value of the function at 1. So f of 1 is 2. Now the limit as x approaches 1 of f of x, let me erase this. The limit of f of x as x approaches 1, you can approach 1 from both sides. You can see the function approaches this point right here at -1. So the answer would be -1 here. Now pay attention to this. Just because the limit of f of x is -1 right here doesn't mean the actual value, as I showed right here, is -1. The actual value can be something entirely different. As I said before, if you completely covered up this, if you had no idea what was going on at 1, if this completely was covered up, then you could look at this and say, oh, this function seems to meet at this point right here at -1. And that's what limit means, really. And you can see limit of f of x as x approaches -3. We can approach from the left. You can see it approaches positive infinity. Approaching from the right, it approaches -infinity. And since they're not equal, the limit does not exist.